close your eyes for just a moment. Imagine yourself floating in the vast emptiness of space. There is nothing around you except an infinite canvas of stars stretching in every direction. You feel weightless, peaceful, almost meditative in this cosmic ocean. But then slowly you notice something strange. The stars behind you are beginning to move. They're not just twinkling anymore. They're bending, stretching, forming strange arcs of light that should not exist. And then you see it. Ahead of you, there is a perfect circle of absolute darkness, a void so complete that it seems to swallow not just light, but your very ability to comprehend what you're looking at. This is a black hole, and you are drifting toward it. What happens in the next 1 second will challenge everything you think you know about time, space, and the very atoms that make up your body. But here is where things get truly strange. That 1 second I just mentioned, it is not the same 1 second you experience when you wait for a traffic light to change or when you hold your breath underwater. Near a black hole, 1 second becomes something entirely different, something that will bend your mind before it bends your body. What if I told you that in that single second near a black hole, your friend watching from a safe distance might observe you frozen in place for millions, even billions of years? What if I told you that your feet could age slower than your head by measurable amounts during that 1 second? What if the atoms in your body would begin a process so horrifying that scientists gave it a name that sounds like it belongs in a horror movie? Spaghettification. Yes, you heard that right. Your body would be stretched like a piece of spaghetti, pulled thinner and longer until you become a stream of particles falling into the darkest abyss the universe has ever created. Now, before we take this journey together, before we dive into the most extreme 1 second any human body could ever experience, I want you to do something for me. If you have ever looked up at the night sky and wondered about the mysteries hiding in that darkness, hit that like button right now. If you want to understand what the most brilliant minds in physics have discovered about these cosmic monsters, subscribe to this channel and turn on that notification bell. And here is what I really want to know. Leave me a comment below answering this question. If scientists told you that you could sacrifice yourself to a black hole and somehow transmit data back about what you experienced, would you do it? Would you give up your existence to solve the greatest mystery in the universe? Think about that as we begin this journey together. Let us start by understanding what exactly you would be falling into. Because a black hole is not just some hole in space. It is not an empty pit waiting to swallow things. A black hole is far more strange, far more terrifying, and far more beautiful than anything your imagination has ever conjured. To understand what 1 second near a black hole would do to your body, we first need to understand what creates such a monster in the first place. Let me take you back, way back, yes, to the death of a star. Picture a star, not our sun, but something far more massive. A star perhaps 20 or 30 times the mass of our sun. For millions of years, this giant has been burning hydrogen in its core, fusing atoms together in a constant battle between two forces. On one side, gravity is trying to crush the star inward, trying to collapse all that mass into a single point. On the other side, the energy released from nuclear fusion pushes outward, creating pressure that resists gravity's pull. For millions of years, these two forces exist in perfect balance. The star shines, it burns, it lights up the cosmos around it, but nothing lasts forever. Eventually the star runs out of hydrogen. Then it starts burning helium, then carbon, then oxygen. It burns through heavier and heavier elements, desperately trying to keep that outward pressure going. But when it reaches iron, something catastrophic happens. Iron cannot be fused to release energy. Instead, fusing iron requires energy. The star has reached the end of its fuel. In that moment, gravity wins. Gravity has been waiting patiently for millions of years, and now nothing stands in its way. The core of the star collapses inward at nearly a quarter of the speed of light. Try to imagine that. Material falling inward at 70,000 kilometers per second. The outer layers of the star come crashing down on this collapsing core, and when they hit, they bounce back in the most violent explosion the universe has ever known. A supernova. For a brief moment, this dying star outshines entire galaxies. It releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. But while the outer layers are being blown away into space, something terrifying is happening at the center. The core keeps collapsing. If the core is massive enough, nothing can stop this collapse. not the pressure of electrons, not the pressure of neutrons, nothing. The core collapses past the point where it becomes a neutron star. It keeps going. It collapses into a single point of infinite density, a point that takes up zero volume but contains all the mass of the original core. This point is called a singularity, and the region of space around it where gravity becomes so strong that nothing, not even light traveling at 300,000 kilometers per second, can escape, that is what we call a black hole. Now here is something that might surprise you. A black hole is not actually a physical object in the way you might think. You cannot touch the surface of a black hole because there is no surface. What exists is that singularity at the center, that point of infinite density, and around it there is a boundary called the event horizon. The event horizon is not a physical barrier. There is no wall there, no membrane, no surface you would bump into. The event horizon is simply the point of no return. It is the distance from the singularity at which the escape velocity equals the speed of light. Inside this boundary, you would need to travel faster than light to escape. And since nothing can travel faster than light, nothing can escape. Not matter, not radiation, not information, nothing. Once you cross that invisible line, your fate is sealed. You will meet the singularity. There is no other option. Every possible path through space-time leads to the center. This is what you are falling toward. This is what 1 second of your life will be spent approaching. But black holes are not all the same. This is crucial to understanding what would happen to your body. There are different types of black holes, and the experience of falling into each type would be dramatically different. Stellar black holes are the ones created by dying stars, and they typically have masses between 5 and 100 times our Sun. They might seem massive, but in cosmic terms they are relatively small. The event horizon of a stellar black hole might only be a few kilometers across. Then there are supermassive black holes, the titans that lurk at the centers of galaxies. These monsters contain millions or even billions of times the mass of our Sun. The supermassive black hole at the center of our own Milky Way galaxy, called Sagittarius, a star, contains about 4 million solar masses. Its event horizon is about the size of Mercury's orbit around the Sun, but that is nothing compared to the largest black holes we have discovered. TON 618, one of the most massive black holes known, contains approximately 66 billion solar masses. Its event horizon would extend far beyond our entire solar system. Why does size matter so much for your experience? Because the size of a black hole determines how quickly the gravitational force changes over distance, and that rate of change is what will ultimately determine how you die. Now let me introduce you to one of the most important concepts you need to understand before we take that fateful 1-second journey. I need to tell you about space-time. You might think of space and time as two separate things. Space is where things happen. Time is when things happen. But in 1915, Albert Einstein showed us that this view is completely wrong. Space and time are not separate. They are woven together into a single fabric called space-time. Everything that exists within this 4-dimensional fabric. You, me, the Earth, the stars, everything. And here is where it gets interesting. Mass and energy do not just exist within space-time. They actually bend it. They curve it. They warp it. Imagine a stretched rubber sheet. If you place a heavy ball in the middle, the sheet curves downward around the ball. Now if you roll a marble across that curved sheet, the marble will not travel in a straight line. It will curve toward the heavy ball. This is roughly how gravity works, though the analogy is imperfect because it only shows 2 dimensions and relies on gravity itself to make the ball sink into the sheet. But it gives you an intuition for what is happening. Massive objects curve space-time around them, and other objects follow those curves. What we experience as the force of gravity is actually objects following the natural curves of space-time. Now imagine what a black hole does to space-time. A black hole curves space-time so severely that at the event horizon, space and time essentially switch roles. Inside the event horizon, moving toward the singularity is not like moving through space anymore. It becomes like moving through time. And just as you cannot stop moving forward in time, you cannot stop moving toward the singularity. This is why escape is impossible. It would be like trying to travel backward in time. The singularity is not just a place in space you are falling toward. It becomes a moment in time that you cannot avoid. Your future inevitably contains the singularity, no matter what you do. This warping of space-time also creates one of the most mind-bending effects you will experience during your 1 second near a black hole. time dilation. You may have heard that time passes differently depending on your speed or your location in a gravitational field. This is not science fiction. This is measured, verified, undeniable fact. The GPS satellites orbiting Earth right now experience time slightly differently than we do on the surface. They are higher up, further from Earth's mass, and so gravity is weaker for them. Time runs slightly faster for the satellites than it does for us. The difference is tiny, just a few microseconds per day, but if we did not account for it, GPS would become useless within hours. The error would accumulate and your navigation system would send you to the wrong location. Now imagine this effect amplified millions, billions, trillions of times. That is what happens near a black hole. As you approach the event horizon, time for you begins to slow down dramatically relative to the rest of the universe. This creates a profound and disturbing paradox. Let us say you have a friend watching you fall from a safe distance. Let us call her Sarah. Sarah has a powerful telescope and she is tracking your descent toward the black hole. As you get closer and closer to the event horizon, Sarah sees something strange happening. You appear to be slowing down. Your movements become sluggish, then barely perceptible. Your radio transmissions become stretched out, your voice dropping to a deep rumble, then becoming a low-frequency radio wave, then stretching beyond detection entirely. The light reflecting off your body shifts from visible colors to infrared, then to radio waves, then to wavelengths so long they cannot be detected. From Sarah's perspective, you never actually cross the event horizon. You get closer and closer, slower and slower, dimmer and dimmer, until you fade from view entirely, but you never cross. Mathematically, it takes an infinite amount of Sarah's time for you to reach the event horizon. She will die of old age, the sun will burn out. The Milky Way will collide with Andromeda, and still, technically, you will not have crossed the event horizon from an outside perspective. You will be frozen there, a fading image burned into the fabric of space-time. But here is the terrifying part. From your perspective, none of this is happening. You're falling normally, you check your watch, and time seems to be passing at its usual rate. You do not feel frozen. You do not even notice anything special when you cross the event horizon, at least not for a large black hole. You simply pass through that invisible boundary without fanfare. The universe has not slowed down for you. Instead, the universe outside has sped up. If you could look back out at the cosmos as you fall, you would see stars being born and dying in rapid succession. You would see galaxies colliding and merging. You would see the entire future of the universe playing out in fast forward. Though in reality, by the time you're close enough to see such effects dramatically, other things would be happening to your body that would make observation rather difficult. Now let us set up our scenario properly. Let us choose our black hole carefully because, as I mentioned, the choice will dramatically affect your experience. For the most educational journey, we're going to imagine two scenarios. First, I will describe what happens if you fall into a stellar mass black hole, one with perhaps 10 times the mass of our Sun. Then I will describe the different experience of falling into a supermassive black hole like the one at the center of our galaxy. And the difference between these two experiences is the difference between a quick, violent death and a slow, strange journey into the unknown. Let us begin your approach. You're in a small spacecraft, and you have positioned yourself 1 light second away from a stellar mass black hole. 1 light second is about 300,000 kilometers. From here, the black hole is visible only because of the accretion disk around it. This is a swirling vortex of gas and dust that is falling into the black hole, but not quite yet. This material orbits the black hole at tremendous speeds, heated by friction to temperatures of millions of degrees. It glows brighter than 1,000 suns, emitting X-rays and gamma rays that would kill you instantly if you were not protected. The accretion disk is your first warning sign, even from this distance. The radiation is intense. Your instruments are picking up readings that seem almost impossible. The magnetic fields around the black hole are tangled and violent, accelerating particles to nearly the speed of light, shooting them out in twin jets from the poles of the black hole. These jets extend for thousands of light years, carrying more energy than entire galaxies produce. But you're not here for the accretion disk. You're here to understand what happens in that final second. So let us move closer. As you approach, something strange begins to happen to the stars behind the black hole. You've probably seen this effect simulated in movies, but no simulation can quite capture how unsettling it is to experience. The light from distant stars is being bent by the black hole's gravity. Stars that should be hidden behind the black hole are visible because their light is being curved around it. The black hole acts as a gravitational lens, bending light rays that pass near it. As you get closer, you notice that there is a ring of light around the black hole, a photon sphere where light itself is orbiting. Any light that enters this region at just the right angle will orbit the black hole before either falling in or escaping. If you position yourself just right, you could theoretically see the back of your own head, the light from behind you curving all the way around the black hole and returning to your eyes. The event horizon appears as a perfect dark circle, darker than anything you have ever seen. It is not reflecting any light because no light can escape from within it. It is not emitting any light for the same reason. It is a perfect void, a circle of absolute nothing against the backdrop of the distorted universe. As you approach, this dark circle grows larger and larger in your view. The universe behind you becomes compressed, the light from all the stars squeezing together into a smaller and smaller ring around that growing darkness. The closer you get, the more the entire observable universe seems to compress into a ring of light surrounding your black prison. Now let us talk about what is happening to your body as you approach. Even before you reach the event horizon, you begin to feel something strange. It starts as a subtle discomfort, almost like the feeling of being stretched when you wake up in the morning. But it does not go away, it gets stronger. This is the beginning of tidal forces acting on your body. Tidal forces are the difference in gravitational pull between different parts of an object. Even here on Earth, the moon's gravity pulls on the side of Earth facing it slightly more than it pulls on the center, and slightly more on the center than on the far side. This difference is what creates ocean tides. Near a black hole, these tidal forces are millions of times stronger. The gravity pulling on your feet is significantly stronger than the gravity pulling on your head, assuming you are falling feet first. This difference stretches you. At first, it is uncomfortable. Then it becomes painful. Then it becomes excruciating. For a stellar mass black hole, this is where your 1 second becomes a nightmare. The tidal forces increase exponentially as you approach the event horizon. Long before you actually reach that point of no return, you're being stretched beyond what human tissue can endure. Your spine begins to elongate, your vertebrae separate, the discs between them rupture, your muscles, which are trying to hold your body together, begin to tear. The pain is unimaginable, assuming your nerve cells can even transmit signals fast enough for you to feel it. Your internal organs are being pulled in different directions. Your heart, your lungs, your liver, all stretching, deforming, failing. Blood pools in your lower body because it is being pulled more strongly toward the singularity. Your brain, receiving less blood, begins to lose consciousness. But the stretching continues whether you are awake or not. This process, this cosmic torture rack, is what scientists call spaghettification. It is not a joke name. It is a precise description of what happens. Your body is stretched thinner and thinner, longer and longer, like a piece of dough being pulled into a strand of pasta. Eventually, you are stretched so thin that individual molecules begin to separate. Your atoms, the very building blocks of your existence, are torn apart from each other. You become a stream of particles, a river of what used to be human, falling into the darkness. For a stellar mass black hole, spaghettification begins before you even reach the event horizon. The tidal forces are so strong at such great distances that you are destroyed while still in observable space. Sarah, watching from her safe distance, would see you being stretched and torn apart, though the image would be redshifted and slowed, creating a haunting, slow-motion death that seems to take forever from her perspective. But let me now describe what happens if you fall into a supermassive black hole. This is a very different experience, and in some ways it is even more terrifying because it is slower and stranger. Remember that tidal forces depend not just on how strong gravity is, but on how quickly it changes over distance. For a supermassive black hole, the event horizon is so far from the singularity that the change in gravity over human body lengths is relatively gentle. This means that you can actually cross the event horizon of a supermassive black hole without being spaghettified. You would survive the crossing. Let that sink in. You would pass the point of no return, the boundary from which nothing can escape, and you would be alive and conscious when you did it. As you approach a supermassive black hole, the tidal forces are barely noticeable at first. The accretion disk is larger, more diffuse, perhaps less deadly if you approach from the right angle. The gravitational lensing effects are similar, but on a grander scale. The dark circle of the event horizon looms before you, but it is not violent. It is almost peaceful. You have time to contemplate what is happening. You have time to feel the philosophical weight of your situation. You're about to cross a boundary from which there is no return. Every person you have ever known is now permanently in your past. Every place you have ever been is now forever unreachable. The entire universe, everything that exists, is about to be separated from you by an impassable barrier, and then you cross. The event horizon passes over you, or perhaps it is more accurate to say you pass through it. And you notice nothing special in that moment. There is no membrane to break through. There is no wall to pass. There is just the continued falling into darkness. But everything has changed. You are now inside a black hole. You are in a region of space-time from which nothing can escape. Your fate is sealed. The singularity awaits. After crossing the event horizon of a supermassive black hole, you have time. Perhaps seconds, perhaps minutes, depending on the size of the black hole and your exact trajectory. Time to think. Time to observe. Time to experience something no human has ever experienced before. What would you see? This is where physics gets speculative, but we have some educated guesses. Looking outward, back toward the universe you left behind, you would see a shrinking circle of light. All the light from the entire universe, compressed into a smaller and smaller disk above you. This disk would be blue-shifted, the light gaining energy as it falls toward you. The stars would appear brighter, shifted toward the blue end of the spectrum. If you could survive long enough, you might see the universe age rapidly, watching the future unfold in fast forward as the blue-shifted light carries information from what seems like accelerated time. Looking inward, toward the singularity, is harder to predict. The singularity is hidden behind a region of extreme space-time curvature. The light from that direction, if there is any, would be redshifted to the point of invisibility. You might see only darkness below you, a darkness even more complete than the darkness of the event horizon from outside, or you might see something stranger. Some physicists speculate about a blue ring of fire, light trapped in the photon sphere that fell in after you, orbiting the singularity before meeting its end. Others suggest you might see nothing at all, your vision failing as space-time itself becomes too warped to carry light in any meaningful way. But even in a supermassive black hole, spaghettification eventually comes. As you fall deeper, getting closer to the singularity, the tidal forces increase. They were gentle at the event horizon, but they grow stronger with every passing moment. The stretching begins. Your body elongates. The same horrifying process I described earlier begins to unfold, but you are already inside the black hole. You are already past the point of no return. There is no one outside who can see this happening. Sarah, watching with her telescope, sees only your frozen image at the event horizon, slowly fading to nothing. She will never know what you experience in these final moments. The spaghettification accelerates. Your body stretches. Your bones break. Your organs fail. Your cells separate. Your molecules are torn apart. And then finally your atoms themselves are pulled to pieces, the electrons stripped from nuclei, the protons and neutrons dissolved into quarks, and perhaps the quarks themselves breaking down into something more fundamental, something we do not yet have the physics to describe. You become a stream of pure information, falling toward a point of infinite density, a place where our understanding of physics completely breaks down. What happens at the singularity? This is the ultimate question, and it is one that physics cannot currently answer. General relativity predicts that the singularity is a point of infinite density and zero volume, but physicists believe this is a sign that the theory is incomplete. Infinities in physics usually indicate that we are missing something, that a more complete theory would give a finite answer. We need a theory of quantum gravity to understand what really happens at the singularity, and we do not yet have one. String theory, loop quantum gravity, and other approaches offer tantalizing hints, but none have been confirmed by experiment. Some theories suggest that instead of a point of infinite density, there is a region of extreme but finite density called a Planck star, where quantum effects prevent complete collapse. Others suggest that matter falling into a black hole might emerge somewhere else, perhaps in another universe through a white hole, a hypothetical object that is the time reverse of a black hole, spewing matter out rather than pulling it in. Some propose that the interior of a black hole is a bouncing cosmology, a universe in its own right that expands and contracts. The truth is, we simply do not know. What we do know is that whatever happens at the singularity, it is unlike anything else in the known universe. Now, I want to take you back to that concept of 1 second and really make you understand how strange time becomes near a black hole. Let us be very precise about what we mean by 1 second. Whose second? Measured how? Near a black hole, these questions matter enormously. Let us say that you are falling toward the black hole and you set a timer on your watch. You start it when you are 1 light second away, and you watch it count down. From your perspective, as you fall, your watch seems to be running normally. 1 second passes, 2 seconds, 3 seconds. Your heart beats at its normal rate. Your thoughts flow at their normal speed. Nothing seems unusual about the passage of time, but here is the thing. What you experience as 1 second is not 1 second for the rest of the universe. Let us consider a specific moment in your fall. Let us say there is a particular position, a certain distance from the event horizon, where you spend what feels like 1 second of your subjective time. During that 1 second of your experience, how much time passes for Sarah, watching from a safe distance? It depends on exactly where you are. If you're relatively far from the black hole, the time dilation might be small. Maybe Sarah experiences 1.1 seconds while you experience 1 second. But as you get closer, the ratio increases. When you are close to the event horizon, the dilation becomes extreme. During 1 second of your time, Sarah might experience minutes, hours, days, years. As you approach the event horizon asymptotically, the ratio approaches infinity. 1 second of your time corresponds to infinite time for Sarah. This is why she never sees you cross. By the time 1 second of your time near the event horizon has passed, an infinite amount of time has passed in the outside universe. From her perspective, you freeze in time. Now consider this thought experiment, which illustrates just how bizarre this situation is. Imagine you have a very powerful laser pointer, and as you fall toward the black hole, you shine it back at Sarah. You turn it on for 1 second of your time, then turn it off. What does Sarah see? As you get closer to the event horizon, the light from your laser becomes red-shifted. Red light stretches to infrared. Infrared stretches to microwaves. Microwaves stretch to radio waves. The 1 second pulse you sent becomes stretched in time. Sarah might detect that 1 second pulse as a signal lasting years, growing weaker and weaker as the wavelength stretches beyond her ability to detect it. Eventually, the light from your laser becomes so red-shifted that no detector can measure it. You have effectively disappeared from the observable universe, even though from your perspective, you are still falling, still alive, still experiencing time. There is something deeply profound about this asymmetry. You and Sarah are both right about how much time is passing. There is no preferred reference frame in general relativity. From your perspective, time is flowing normally, and Sarah's time is running infinitely fast. From her perspective, time is flowing normally and your time has stopped. Both are valid descriptions of reality. Time itself is not absolute. It is personal. It depends on where you are and how you are moving. This is not a matter of clocks running at different speeds. The actual passage of time, the aging of cells, the flow of thoughts, the experience of existence, all of it runs at different rates depending on your position in a gravitational field. Let me pause here and ask you something. Have you ever felt like time was moving too fast or too slow? Those moments when you're having fun and hours seem like minutes? Or when you're bored and minutes seem like hours? We tend to think of these as psychological illusions, and in normal life they are. But near a black hole, the distortion of time is not psychological. It is physical. It is real. The very fabric of space-time is warped so severely that time flows at genuinely different rates. If this is fascinating to you, if this is making you think about the universe in a new way, take a second right now to hit that like button. Share this video with someone who loves thinking about the big questions, and subscribe if you want to keep exploring the strangest phenomena in the cosmos with me. Now, let us talk about what you would actually see during your 1 second near a black hole. I've described the theoretical physics, but what would the visual experience be like? This is something that has been simulated by physicists using supercomputers, and the results are genuinely stunning. As you approach a black hole, the first thing you notice is that the sky looks wrong. Stars that should be in fixed positions relative to each other are moving. Not moving like the Earth's motion makes stars appear to shift over months. but moving dramatically, changing positions as you watch. This is because the black hole is bending the light from those stars. Each star's light is taking a curved path to reach your eyes, and as you change your position relative to the black hole, the amount of bending changes, making the star appear to move. The black hole itself appears as a perfect circle of darkness, but it is surrounded by strange light effects. There is the accretion disk, if one exists, which appears warped and twisted by the gravitational lensing. You can see the back of the accretion disk bent around the black hole, appearing above it like a strange glowing halo. There is also the photon sphere, that region where light orbits the black hole. This creates a bright ring around the dark circle, the famous image captured by the Event Horizon telescope when it photographed the black hole at the center of the galaxy M87. As you get closer, the dark circle of the event horizon grows larger and larger in your visual field. At the same time, the sky behind you compresses. All the light from the universe you are leaving behind gets squeezed into a smaller and smaller circle above you. The darkness below grows, the light above shrinks. Eventually, more than half of your visual field is just blackness. The event horizon filling your view like an endless floor of nothing below you. If you're falling into a stellar mass black hole, you might not have much time to appreciate this view. The spaghettification process causes your eyes to distort, your brain to lose blood, your consciousness to fade. But if you're falling into a supermassive black hole, you might have minutes to watch this cosmic light show. You might see the entire visible universe compressed into a point above you, a single blinding spot of light containing everything that ever existed, will exist, or could exist outside the prison you are entering. After crossing the event horizon, the visual experience becomes even stranger and more speculative. Looking up, back toward the universe, you see what some physicists call the anti-horizon, a bright boundary representing the event horizon seen from the inside. All the light that falls into the black hole after you is compressed along this boundary. Looking around you, space-time is so warped that traditional concepts of direction start to break down. Where is up? Where is down? These questions begin to lose meaning as the geometry of space itself becomes alien to human experience. I want to take a moment here to discuss something that might seem like a tangent but is actually crucial to understanding what 1 second near a black hole means. I want to talk about consciousness and the experience of time. When we ask what 1 second near a black hole does to your body, we are implicitly asking about your experience of the second. But what is experience? What is consciousness? These are questions that neither physics nor neuroscience has fully answered. We know that consciousness requires a functioning brain, and that brain activity takes time. Neurons fire at certain rates. Chemical signals propagate at certain speeds. Thoughts, perceptions, and experiences all take time to process. Near a black hole, as your body is being spaghettified, as your brain is being stretched and starved of blood, what happens to your consciousness? This is genuinely unknown. Perhaps consciousness fades quickly as the brain loses function. Perhaps there are strange effects as neurons are stretched, causing bizarre hallucinations or perceptions. Perhaps, in those final moments, as your brain cells separate and your neurons elongate, there is a kind of cosmic experience that no human has ever had and no human can describe because no one has returned to tell us about it. Some physicists have speculated about what might be called a last observer effect. The idea is that as you fall toward the singularity, time dilation becomes extreme. In your final moments, as you approach the singularity, an infinite amount of time might pass in the outside universe. In theory, you might experience the entire future history of the cosmos in your last moments of consciousness. You might see the stars burn out, galaxies fade, protons decay, and the universe approach its final state of heat death, all in a subjective instant. This is highly speculative and likely wrong, but it gives a sense of how strange the experience of time near a black hole truly is. Let us now turn to a question that might have been bothering you. If nothing can escape a black hole, how do we know anything about what happens inside? This is an excellent question, and the answer comes from the power of physics and mathematics. We cannot directly observe the inside of a black hole. No signal can reach us from beyond the event horizon. But we can calculate what should happen based on our understanding of general relativity. We can run computer simulations. We can use mathematical models to predict what an infalling observer would experience, and remarkably, our predictions are consistent. Different physicists using different methods arrive at the same conclusions about spaghettification, time dilation, and the journey toward the singularity. Moreover, we can observe effects that tell us about the extreme gravity near black holes. We can see stars orbiting close to black holes, moving at incredible speeds that match our predictions. We can detect gravitational waves, ripples in space-time created when black holes merge, and these waves match our calculations with stunning precision. We can image the shadow and accretion disk of black holes, as the Event Horizon Telescope has done, and these images match our simulations. Every observation we make confirms that general relativity accurately describes gravity near black holes. This gives us confidence that our predictions about what happens inside, while not directly verifiable, are likely correct. There is another piece of physics I need to explain because it is relevant to your 1-second experience. I need to tell you about Hawking radiation. In 1974, Stephen Hawking made a stunning theoretical discovery. Black holes are not completely black. They emit radiation and slowly evaporate over time. This seems to contradict everything I have told you about nothing being able to escape a black hole. So let me explain how it works. The key is quantum mechanics. In the quantum vacuum, even in empty space, particle-antiparticle pairs are constantly popping into existence and then annihilating each other. These are called virtual particles. Normally they appear and disappear so quickly that they do not affect anything. But at the event horizon of a black hole, something strange can happen. A particle-antiparticle pair can form with one particle just inside the event horizon and one just outside. The particle inside falls in. The particle outside escapes. From a distance, it looks like the black hole is emitting particles. This is Hawking radiation. The energy for these particles has to come from somewhere, and it comes from the black hole itself. Each particle that escapes carries away a tiny bit of the black hole's mass. Over incredibly long times, this causes the black hole to shrink and eventually evaporate entirely. For stellar mass black holes, this process takes longer than the current age of the universe, so it is practically irrelevant for your 1-second journey. But it is theoretically important because it raises deep questions about information. When you fall into a black hole, you carry information with you. The arrangement of atoms in your body, your memories encoded in your neurons, the pattern of particles that makes you uniquely you. What happens to that information? According to quantum mechanics, information cannot be destroyed. But if you fall into a black hole, and the black hole eventually evaporates through Hawking radiation, where does your information go? For decades, this was known as the black hole information paradox, and it sparked fierce debate among physicists. The current best understanding, though it remains controversial, is that information is not destroyed, but is encoded in subtle correlations in the Hawking radiation. In principle, if you could collect all the Hawking radiation emitted by a black hole over its entire lifetime and decode it perfectly, you could reconstruct the information about everything that fell in, including you. You would not be alive again, but the information that constituted your existence would not be lost. Hey, this is a deep and profound idea. In some sense, your pattern, your information, your essence might survive the black hole, encoded in radiation scattered across the cosmos. But let us bring this back to your subjective experience. During that 1 second near the black hole, you do not care about information paradoxes or Hawking radiation. You care about what is happening to your body and your mind. So let me take you through the experience one more time, now with all the physics context we have built up. You begin your journey 1 light second from a stellar mass black hole. At this distance, the gravitational effects are already noticeable but not yet deadly. You feel a slight stretching, a discomfort in your joints. The black hole appears as a dark circle against the warped starfield. The accretion disk, if present, glows violently around it. Your instruments are screaming warnings about radiation levels and gravitational anomalies, but you press on. As you fall closer, the stretching increases. It transitions from discomfort to pain. Your body is being pulled in 2 directions, your feet toward the singularity, your head away from it. The blood in your body begins to redistribute, pooling in your lower extremities. Your heart works harder to pump blood to your brain, but the gravitational gradient is fighting it. You begin to feel lightheaded, your vision starts to narrow. The black hole is no longer just a feature of the landscape, it dominates your view, it is consuming your reality. The light from the stars behind you begins to compress into a ring, then a point. The darkness below expands. You are falling faster now. The acceleration no longer measured in comfortable human units, but in multiples of Earth's gravity. 10 Gs, 100 Gs, 1,000 Gs. Your body cannot withstand these forces. Your spine has begun to separate. Your ribs are breaking. Your skin is stretching beyond its elastic limit, tearing. Your organs are failing, crushed and stretched beyond function. And then, in that final fraction of your subjective second, spaghettification completes. You are no longer a human being. You are a stream of particles, a river of atoms falling toward oblivion. Your consciousness, whatever it was, is gone. Your experience has ended. But from Sarah's perspective, you are still there. A frozen, fading image at the edge of the event horizon. She will watch you dim for years, decades, centuries, until the last photon from your dying form is redshifted beyond detection. And even then, mathematically, you have not crossed. You are forever falling, forever dying, forever frozen at the boundary of the abyss. Now let me take you through the alternative scenario. You are falling toward a supermassive black hole, one with 4 million solar masses, like Sagittarius A star at the center of our galaxy. The approach is different. The accretion disk, if present, is more diffuse. The tidal forces are gentler. You can approach the event horizon without being torn apart. The experience is almost meditative. You have time to contemplate the enormity of what is happening. As you fall, the time dilation effects are similar. Sarah sees you slow down and redshift. But from your perspective, you are falling freely. The universe is becoming strange around you. Light is bending in ways that make the sky look like a funhouse mirror. The dark circle of the event horizon grows, but it grows slowly enough that you can watch it happen. You have minutes, not seconds, to prepare for what comes next. And then you cross. The event horizon passes over you like a shadow, like a ghost. You feel nothing in that moment. There is no barrier, no sensation, no dramatic event. One moment you're outside, part of the observable universe. The next moment you're inside, forever separated from everything you knew. The transition is silent. It is invisible. It is the most profound boundary in the universe, and crossing it feels like nothing at all. After crossing, you continue to fall. The singularity is still far away. You have time, perhaps minutes, to exist inside the black hole. What do you see? What do you experience? This is where physics becomes uncertain. The space-time geometry inside a black hole is so warped that our intuitions fail completely. Looking up, you see a shrinking disk of light, the entire observable universe compressed into a smaller and smaller circle above you. Looking down, there is only darkness, the singularity hidden behind the extreme curvature of space. As you fall deeper, the tidal forces begin to increase. The gentle giant is revealing its true nature. The stretching begins. Your body elongates. Your spine separates. The same horrible process that happened outside the stellar black hole now happens inside the supermassive one, but no one can see it. Sarah sees only your frozen image at the event horizon, slowly fading. She will never know the horror of your final moments. In those last instants, as your body is torn apart and your consciousness fades, you might experience something truly strange. Time dilation becomes extreme near the singularity. Your subjective experience of time might stretch in unexpected ways. Some theorists speculate about a kind of eternal moment, a final instant of consciousness stretched by time dilation into something subjectively longer. Others dismiss this as nonsense, pointing out that the brain cannot function when it is being spaghettified. The truth is, we do not know. And unless we develop a theory of quantum gravity that makes testable predictions about the interior of black holes, we may never know. What happens at the singularity itself is completely unknown. Our physics breaks down. General relativity predicts infinite density, but physicists believe this is a sign that the theory is incomplete. Something happens at the singularity, but we do not know what. Your atoms, your quarks, the fundamental particles that made up your body meet their final fate there. Perhaps they are destroyed. Perhaps they are transformed. Perhaps they pass through to somewhere else entirely. The singularity is the ultimate mystery, the final frontier of physics, and your 1 second journey ends there in the heart of the unknown. I want to take some time now to discuss what scientists have actually observed about black holes. Because everything I have told you is not just theoretical speculation. It is grounded in observations and experiments that confirm our understanding of these cosmic monsters. The most dramatic confirmation came in 2019 when the Event Horizon Telescope collaboration released the first ever image of a black hole. This was not a photograph in the traditional sense. It was constructed from radio wave observations made by telescopes all around the world, combined using a technique called very long baseline interferometry. The resulting image showed the shadow of the black hole at the center of the galaxy M87, a monster containing 6.5 billion solar masses. The shadow, a dark circle surrounded by a ring of light, matched our theoretical predictions with remarkable precision. In 2022, the same collaboration released an image of Sagittarius, a star, the supermassive black hole at the center of our own Milky Way galaxy. This was an even more difficult achievement because our galaxy's central black hole is much smaller, and its image flickers on short timescales. But again, the image matched our predictions. The dark shadow, the bright ring, the gravitational lensing, all were consistent with general relativity's description of black holes. We have also detected black holes through gravitational waves. When two black holes orbit each other and eventually merge, they send ripples through spacetime. These ripples, gravitational waves, were first detected by the LIGO Observatory in 2015, exactly 100 years after Einstein predicted their existence. Since then, we have detected dozens of black hole mergers. Each detection confirms our understanding of how black holes behave, how they distort spacetime, and how they interact with each other. The gravitational wave signals match our predictions with stunning accuracy, providing powerful evidence that our theories about black holes are correct. We have observed stars orbiting close to black holes, moving at incredible speeds. The stars at the center of our galaxy orbit Sagittarius A star at speeds of thousands of kilometers per second. Their orbits have been tracked for decades, and they perfectly match the predictions of general relativity. One star, called S2, passed within 20 billion kilometers of the black hole in 2018, traveling at nearly 3% of the speed of light. Observations of this close approach detected the effects of gravitational redshift and time dilation, confirming Einstein's predictions. All of this observational evidence gives us confidence that our theoretical understanding of black holes is correct, at least in the regions we can observe. The regions we cannot observe, inside the event horizon, near the singularity, remain mysterious. But the remarkable success of general relativity in every testable prediction gives us confidence that its predictions about the interior are likely correct as well. Now I want to address something that might be on your mind. Why should you care about black holes? What does this have to do with your daily life? This is a fair question. Black holes are exotic objects, far from Earth, seemingly irrelevant to human concerns. But I would argue that understanding black holes is deeply important for several reasons. First, black holes teach us about the fundamental nature of reality. They are places where our understanding of physics is pushed to its limits. The extreme conditions near a black hole force us to confront the deepest questions about space, time, matter, and information. By studying black holes, we learn about the universe at its most fundamental level. We push the boundaries of human knowledge. We expand our understanding of what is possible. Second, black holes are everywhere. They are not rare objects hiding in distant corners of the universe. There is a supermassive black hole at the center of virtually every large galaxy, including our own. There are stellar mass black holes scattered throughout galaxies, the remnants of dead stars. Some estimates suggest there are tens of millions of black holes in our galaxy alone. Black holes are a fundamental part of how the universe works. They shape the evolution of galaxies. They create some of the most energetic phenomena in the cosmos. Understanding them is essential to understanding the universe we live in. Third, black holes inspire us. They remind us that the universe is stranger, more wonderful and more terrifying than we could ever imagine. They challenge our intuitions. They force us to think deeply about concepts that seem simple, but turn out to be profound. Concepts like time, space, and existence. When you contemplate what 1 second near a black hole would do to your body, you're engaging with the deepest questions humanity has ever asked. You are participating in the grand adventure of scientific inquiry. Let me now discuss some of the more speculative ideas about black holes. Things that go beyond established physics into the realm of theoretical possibility. One of the most fascinating is the idea that black holes might connect to other places. The mathematics of general relativity allows for the existence of wormholes, hypothetical tunnels through spacetime that connect distant points. Some theorists have speculated that the interior of a black hole might connect to a wormhole, allowing passage to another location or even another universe. However, even if wormholes exist inside black holes, they would not be traversable by humans. The journey to the singularity involves being spaghettified. You could not survive the passage through the wormhole even if it existed. Moreover, most physicists believe that any wormhole that might exist inside a black hole would be unstable, collapsing before anything could pass through. The idea of using black holes for interstellar travel, as depicted in some science fiction, is almost certainly impossible. Another speculative idea involves the holographic principle. This is the idea that all the information about what happens inside a region of space can be encoded on the boundary of that region. Some physicists have proposed that the three-dimensional interior of a black hole might be entirely encoded on the two-dimensional surface of the event horizon. In this view, the interior of a black hole might not exist as a separate region at all. What falls in might be spread across the event horizon in a kind of cosmic hologram. This idea is highly speculative and controversial, but it offers a potential resolution to the information paradox and might eventually lead to a theory of quantum gravity. Yet another speculative idea is that black holes might create new universes. The singularity at the center of a black hole is a point of extreme conditions, possibly similar to the conditions at the Big Bang that created our universe. Some theorists have proposed that the singularity might be a kind of cosmic birth, the beginning of a new space-time that inflates into a separate universe. In this view, every black hole might contain a universe, and our universe might exist inside a black hole in some larger cosmos. This idea is untestable with current technology, but it is a beautiful example of how studying black holes leads us to contemplate the deepest questions about existence. I want to take a moment to reflect on the philosophical implications of what we have discussed. When you consider what 1 second near a black hole does to your body, you are confronting the limits of human existence. You are facing the reality that the universe is not built for human comfort. The cosmos contains objects and conditions so extreme that human life is impossible. This might seem depressing, but I find it oddly comforting. It puts our daily concerns in perspective. Our worries, our conflicts, our struggles, all of them occur on a tiny blue planet orbiting an ordinary star in an unremarkable corner of an average galaxy. The universe is vast beyond comprehension, filled with wonders and horrors that dwarf anything we can imagine. And yet, here we are, tiny creatures made of atoms forged in the hearts of dead stars, contemplating the nature of reality, sending telescopes into space to photograph black holes, detecting ripples in the fabric of space-time caused by collisions billions of light-years away. Human beings are remarkable. Our existence is unlikely. Our curiosity is boundless. Our capacity for understanding is inspiring. When you contemplate a black hole, you are participating in one of the most profound activities possible. You're using your mind, that extraordinary collection of neurons, to understand the universe that created you. Let me bring us back to the personal experience one more time. I want you to really feel what that 1 second might be like, as much as it is possible to feel something so alien through words on a screen or sounds from a speaker. Close your eyes for a moment. Imagine yourself floating in space. Approaching the event horizon of a black hole, feel the subtle stretching in your body, the discomfort that grows into pain. Watch the universe around you distort, stars bending and shifting, the sky compressing into a ring of light above you. Feel the acceleration, the inexorable pull toward the darkness below. Know that there is no escape, no rescue, no hope. You're falling into oblivion, and the only question is what you will experience on the way down. Now, imagine the final instant. Your body stretched to its breaking point and beyond, your atoms separating, your consciousness, that mysterious phenomenon that makes you you, flickering and fading. What is your last thought? What is the final experience of a mind being spaghettified? No one knows. No one can know. But the question itself is profound. It forces us to confront our mortality, our fragility, our place in the cosmos. There is something almost religious about contemplating black holes. They are places of ultimate mystery, where our understanding fails and our imagination reaches its limits. They are objects of terrible power and strange beauty. They are the closest things the universe has to cosmic deities, entities of unimaginable gravity that shape the fate of stars and galaxies. And yet they are natural. They follow the laws of physics. They are comprehensible, at least in part, through the extraordinary power of human reason. I have been talking for a long time about what 1 second near a black hole does to your body, and I realize I should address the question of why 1 second specifically. The choice of 1 second is somewhat arbitrary, but it has a certain poetic resonance. 1 second is a human timescale, a heartbeat, a breath, a moment of conscious experience. It is long enough to be meaningful but short enough to be comprehensible. And as we have seen, near a black hole, 1 second becomes something much more than a simple unit of time. It becomes a window into the strangeness of the universe. Near a black hole, 1 second can contain eternities. 1 second can stretch across billions of years of external time. 1 second can encompass your transformation from a living, thinking human being into a stream of particles falling into the unknown. 1 second, in the right conditions, can be the difference between existence and oblivion. This is the power of extreme gravity. This is what Einstein's equations tell us about the universe. Time is not absolute. It is personal, local, dependent on where you are and how you are moving. Near a black hole, this dependency becomes dramatic, undeniable, inescapable. 1 second for you is not 1 second for me, and in that simple statement lies a revolution in our understanding of reality. Before I conclude, I want to share some thoughts about the future of black hole research. We are living in a golden age of observational astronomy. The Event Horizon Telescope continues to improve, planning to add more telescopes and observe more black holes with higher resolution. The LISA mission, a space-based gravitational wave detector, is planned for the 2030s and will detect gravitational waves from supermassive black hole mergers, opening a new window on the universe. New X-ray and gamma-ray telescopes will observe the violent environments around black holes with unprecedented detail. On the theoretical side, physicists continue to work on the problem of quantum gravity. String theory, loop quantum gravity, and other approaches offer glimpses of what a complete theory might look like. If and when we develop such a theory, we will finally understand what happens at the singularity, what happens to information that falls into a black hole, and what the true nature of spacetime is at the smallest scales. We may never be able to send a human into a black hole and receive data back. The laws of physics seem to forbid it. But we can learn about black holes through observation, calculation, and imagination. We can push the boundaries of knowledge without crossing the boundary of the event horizon. And in doing so, we can satisfy that most human of impulses, the desire to understand. So where does this leave us? We have taken a journey together, from the death of a star to the birth of a black hole, from the warping of space-time to the stretching of a human body, from the event horizon to the singularity. We have explored what physics tells us about the most extreme environments in the universe. We have contemplated time dilation, spaghettification, information paradoxes, and the limits of human knowledge. What 1 second near a black hole does to your body is, in essence, everything. It transforms you from a human being into something else entirely. It takes the familiar experience of time and warps it beyond recognition. It stretches your atoms across distances that should be impossible for a single body. It ends your existence as a person while preserving perhaps some echo of your information in the radiation that slowly evaporates the black hole over eons. But beyond the physical effects, contemplating this 1 second does something to your mind. It expands your perspective. It humbles you before the vastness and strangeness of the cosmos. It reminds you that the universe is not obligated to be comprehensible, but that through the extraordinary power of science, we have made it comprehensible anyway, at least in part. If you have made it this far in this journey, thank you. Thank you for your curiosity, your patience, and your willingness to engage with ideas that are complex and sometimes disturbing. This is what science is about. This is what human inquiry is about. We ask questions that seem impossible to answer, and then we find answers that reveal new questions. We push against the boundaries of the unknown, and in doing so, we expand the realm of the known. So let me leave you with a final thought. Somewhere out there, right now, stars are dying and black holes are being born. Matter is falling into event horizons and being stretched into oblivion. Time is passing at different rates in different places. The universe is strange and beautiful and terrifying beyond measure, And here you are, a collection of atoms arranged in a pattern that allows for consciousness, contemplating it all. That is extraordinary. You are extraordinary. The universe that created you is extraordinary. If this video has made you think, if it has sparked your curiosity, if it has given you a new appreciation for the strangeness of reality, then please share it with someone else who might appreciate it. Hit that like button, subscribe to the channel, leave a comment telling me what part of this journey fascinated you the most, or what questions you still have. The conversation does not end when this video ends. It continues in the comments, in the follow-up videos, in the ongoing human quest to understand the cosmos. Thank you for joining me on this journey. Thank you for taking this 1 second near a black hole with me. And thank you for being curious about the universe we all share. Until next time, keep looking up at the stars. Keep asking questions. Keep pushing the boundaries of what you know. The universe is waiting to be understood, and you are part of the grand adventure of discovery. Remember that somewhere in the cosmos, a black hole is waiting. Its event horizon is a one-way door to the unknown. Its singularity is the ultimate mystery, and while none of us will ever take that final journey in person, we can take it in our minds. We can understand, at least in part, what happens when matter meets the most extreme gravity in the universe. We can comprehend what 1 second near a black hole does to a human body, and in that comprehension, we touch something profound. We connect with the deepest truths about reality. We become, for a moment, part of the cosmic story. This has been an exploration of one of the most extreme phenomena in the universe. From the perspective of physics, we have seen how general relativity predicts the warping of spacetime, the dilation of time, and the stretching of matter near a black hole. From the perspective of human experience, we have imagined what it might be like to fall into oblivion, to have your body torn apart by tidal forces, to watch the universe fade from view as you cross the event horizon. We have discussed stellar mass black holes and supermassive black holes, each offering a different kind of death. We have explored the information paradox and the holographic principle, ideas that push the boundaries of our understanding. We have celebrated the observational triumphs that confirm our theories, from gravitational wave detections to direct images of black hole shadows. And through it all, we have maintained a sense of wonder, because that is what black holes inspire. They are objects of terror and beauty, of destruction and creation, of mystery and revelation. They are the universe at its most extreme. And they remind us that reality is far stranger than we could ever have imagined on our own. So as we conclude this journey, I invite you to carry this sense of wonder with you. When you look up at the night sky, remember that hidden among those points of light are black holes, cosmic monsters that warp space and time. When you think about your own existence, remember that you are made of the same atoms that fall into black holes, that you are part of the same universe that contains these extreme objects. When you contemplate time, remember that it is not absolute, that 1 second can mean different things in different places. The universe is vast and strange and wonderful. Black holes are among its strangest inhabitants, and you, curious human, have spent this time understanding them a little better. That is a remarkable achievement. That is what it means to be a thinking creature in a cosmos that does not owe us any explanations but has, through the power of science, revealed its secrets to us anyway. What 1 second near a black hole does to your body is end your existence as you know it. But what contemplating that 1 second does to your mind is expand it, deepen it, connect it to the profound mysteries of the universe. And that, in the end, is perhaps the greatest gift that science can offer. The darkness of a black hole is complete, but the light of understanding pushes back against it. We may never cross an event horizon, but we can understand what lies beyond. We may never experience spaghettification, but we can describe it with mathematics and physics. We may never touch a singularity, but we can contemplate its nature and work toward theories that will reveal its secrets. This is the human project. This is what we do. We ask questions about the universe, and we find answers. We push against the boundaries of the unknown, and we expand the realm of the known. We are small creatures on a small planet, but our minds can encompass the cosmos. We can understand black holes. We can understand space-time. We can understand what 1 second near a black hole does to a body. And in that understanding, we find something precious. We find meaning. We find connection. We find our place in the cosmic story. We are made of star stuff, as Carl Sagan said, and we are capable of understanding the stars. We are brief flickers of consciousness in an eternal universe, but we are flickers that can comprehend eternity. Thank you for being part of this journey. Thank you for your curiosity and your attention. Thank you for caring about the deep questions, the hard questions, the questions that push us to the limits of understanding. You are what makes this exploration meaningful. Without curious minds to appreciate them, the wonders of the universe would go unwitnessed. But you are here, you are witnessing, you are understanding. And so, as we end, I leave you with this. The universe is strange beyond measure. Black holes are among its strangest phenomena. Time is not what you thought it was. Space is not what you thought it was. Reality is far deeper and more mysterious than everyday experience suggests. But through science, through curiosity, through the remarkable power of the human mind, we can understand these mysteries. We can take 1 second near a black hole, not in body but in mind, and we can know what happens there. That is the gift of science. That is the gift of curiosity. That is the gift of being human in a universe that contains black holes. We can understand. And in understanding, we transcend our limitations. We become, in some small way, part of the cosmic story. This journey has taken us to the edge of a black hole and beyond. It has shown us what 1 second can mean in the most extreme environment the universe has to offer. It has stretched our minds, if not our bodies, across the strange terrain of general relativity and astrophysics. And it has, I hope, left you with a deeper appreciation for the universe we inhabit. Keep asking questions, keep seeking answers, keep looking up at the stars and wondering what lies among them. The universe is waiting to be understood, and you have the power to understand it. 1 second near a black hole would end your body, but a lifetime of curiosity can expand your mind to encompass the cosmos. This is the end of our journey, but it is not the end of the story. The story continues in every question you ask, every wonder you feel, every moment you spend contemplating the deep mysteries of existence. The black holes are out there, waiting, and you are here, understanding. That is something remarkable. That is something worth celebrating. Go forward with curiosity. Go forward with wonder. Go forward with the knowledge that you have touched, in some small way, the edge of the abyss, and you have emerged with understanding. That is the human triumph. That is what makes us extraordinary. The universe is vast and dark, but the light of human understanding illuminates it. 1 second near a black hole would destroy your body, but the knowledge of what that second contains enriches your mind forever. This is the paradox and the beauty of science. We study destruction and find enlightenment. We contemplate oblivion and find meaning. Thank you for taking this journey. Thank you for being curious. Thank you for being human. 1 second near a black hole would be the end of everything you are. But thinking about that 1 second, understanding it, comprehending the physics and the strangeness and the terror and the beauty of it, that is the beginning of something wonderful. That is the beginning of understanding, and understanding in the end is what we are here for. It is what makes the brief flicker of human consciousness worthwhile. It is what connects us to the cosmos and to each other. It is what transforms a terrifying universe into a comprehensible one, a meaningless void into a story we can tell and understand and share. This story, the story of what 1 second near a black hole does to your body, is one chapter in that larger story. It is one window into the strangeness of reality. It is one example of the power of human curiosity and the triumph of human understanding. I hope you have enjoyed this chapter. I hope it has expanded your mind and deepened your appreciation for the universe. I hope it has sparked new questions and new curiosities that will drive you to learn more, to understand more, to push further against the boundaries of the unknown. The journey continues, the questions multiply. The universe reveals its secrets one by one, and each secret reveals new mysteries. This is the adventure of science. This is the adventure of being human, and you are part of it. Thank you for being part of it. Thank you for this time together, and thank you for being curious about what 1 second near a black hole does to your body. The answer, as we have seen, is everything. It does everything. It ends you. It stretches you. It freezes you in the eyes of outside observers. It transforms you into a stream of particles falling into the unknown. It makes 1 second into an eternity, and an eternity into 1 second. It bends your reality until reality itself loses meaning. But it also does something else. It inspires us. It challenges us. It drives us to understand. And in understanding, we become more than we were. We become creatures who can comprehend the incomprehensible, who can face the abyss and describe what we see, who can take 1 second near a black hole and turn it into knowledge that enriches all of humanity. That is what this journey has been about. Not just the physics, not just the destruction, but the understanding. The human understanding that takes the cold equations of general relativity and turns them into meaning, into wonder, into awe. You have that understanding now. You know what 1 second near a black hole does to your body. You know about spacetime and gravity and tidal forces and spaghettification and time dilation and event horizons and singularities. You know about the limits of physics and the frontiers of knowledge. You know about the observational triumphs that confirm our theories and the theoretical mysteries that remain unsolved. You are richer for this knowledge. You see the universe more clearly. You understand your place in it more deeply. That is the gift I hope this journey has given you. That is the gift of science and curiosity and wonder. Take that gift and use it well. Share it with others. Let it inspire you to learn more, to question more, to understand more. The universe is waiting. The black holes are out there, and you, curious human, are ready to face them, not with your body but with your mind. That is enough. That is more than enough. That is everything. The 1 second is over, but the understanding lasts forever. End.